So I will talk about assessing teleconnection pathways with causal inference techniques. And I will talk about this teleconnection, this climate aspect, and then how to use kind of novel techniques from causal inference to understand these. So, when I prepared this talk, I also thought of the target audience, and I guess it is very interdisciplinary. So I will also try to keep this focus of my talk relatively broad. And I'm usually more used to kind of convince climate scientists why they should consider new approaches to study their data. But I will also try to give a rather personal perspective on where the machine learning community might actually help with some problems we face in climate science. And I also want to acknowledge Jakob Runge and Dim Kaumer, they're both here. So I worked a lot with Jakob during my PhD and still work with him, and Dim Kaumer was my PhD supervisor. And is also much involved in using causality in climate science. And I will also present some ongoing work, which I do with Ted Shepard and Redding. Okay, so I want to motivate this topic with this very schematic overview of the different timescales of forecasting. So on the left, we see we have weather forecasting, so time ranges of a few hours or a few days. And on the right side, it's climate projections, so forecasts of the next century. And scientifically, this is, of course, very different problems. So weather forecasting is mostly an initial value problem. We have the initial state of the atmosphere, which gives us the predictability. And after a few days, this signal is lost. And climate projection, it's a boundary condition problem. It depends, or the scale will depend on emission scenarios and so on. But actually, in between, there are, of course, also very relevant timescales. And so we have on the one hand side, we have decadal predictions. So questions like how warm will the next years be in Europe, let's say, or how cold. And then there's this, it was mentioned before, this very relevant sub-seasonal to seasonal timescale. So this is questions like how will the weather be in the next 2 weeks, 3 weeks, up to the season. And these timescales are really relevant for decision makers because most of the most impactful extreme events or weather events are happening on these timescales, like droughts or heavy precipitation, heat waves, and so on. And so this is like a time range where we really need to make progress because decision makers kind of need these reliable information to do some effective adaptation strategies. But right now, this timescales is actually it's also known as the prediction desert. So one reason is, of course, that just historically, most of the scientific effort was focused on weather forecasting and climate projections. The second reason is that we don't know much yet about these different timescales in between. So how can we change this? How can we actually make better predictions? And I will mostly focus here on this S2S timescale. So one very important source of predictability was already mentioned several times again. So this is this famous El Niño Southern Oscillation, or ENSO. And it's probably the best documented mode of variability in the climate system. And if you look here on this red arrow, when we have in this El Niño basin, when we have higher sea surface temperatures in this region, this kind of triggers a wave train into the mid-latitudes. And this changing circulation patterns, these will interfere with the jet stream and the circulation in the mid-latitudes. And this will then also affect the weather there. And actually, ENSO has significant impacts on surface weather across the globe. And this is, exactly what we call a teleconnection. So we have something happening far away in the climate system, but it actually affects also our weather in different regions. Just in this example, the United States. So we have to understand these sources of predictability on these different S2S timescales in order to make better predictions on regional climate and weather. So it's these rather slow-moving components of the climate system which are giving us this source of predictability. And of course, it's not just ENSO, but this is where we have ENSO in the same region. There's also happening on shorter time scales, this Madden-Junian oscillation. There's in the stratosphere we have, in the tropical stratosphere, we have something called the QBO. So this is another oscillation. In the stratosphere, over the Arctic, we have the polar vortex. This is actually my teleconnection, or my favorite teleconnection, and what I looked at mostly during my PhD. Then also there's snow cover and Arctic sea ice, which are all known to kind of can have an impact and kind of shape the PDFs of different weather regimes in one direction. So it's these different components we have to understand to actually improve these forecasts. But this is not simple, as we have heard, because the interactions of these modes are not understood. And they operate on different spatial-temporal timescales. So on the one hand, it's not well understood how they affect different weather regimes, but it's even more complicated how they interact with each other. And so the key task is really to separate the signal, so the teleconnection pattern, from the noise. And the noise is the large atmospheric variability. And this is exactly where hopefully machine learning can help. So and really make a difference, because right now the techniques we have are too limited to achieve this, and also models struggle a lot with representing these different teleconnections. I also picked up these kind of conflict between machine learning and climate physics. And I like this XKCD comic, which is, three scientists talk, and one says, our field has been struggling with this problem for years. And then one says, well, maybe the machine learner says, struggle no more, I'm here to solve with algorithms. And then 6 months later, he finds out that it's actually quite hard. Well, climate scientists like this because it shows them that the climate physics is, of course, still fundamental. And I really don't think that machine learning will solve everything, but I do really think that it's actually good to get an additional perspective on the data we have already. So, I don't know who you think you are in this comic, but I think they're all relevant. So, the machine learning technique I'm mostly interested in is something which is called causal inference, and I think there will be more talks and also posters about this, but I think I'm the first one right now who talks about this. So, so this has nothing to do with deep learning, but it's still machine learning. So it's also something which Judah Pearl, which is the father of causal inference, called the causal revolution. So actually, this very historic question of how to define cause and effect in physics or in science has actually long been neglected in statistics. He explains this very nicely in this recent book, The Book of Why. But actually, there is quite a rigorous mathematical framework to identify these cause-effect relationships. And these concepts are now also more and more applied to climate science, but it's, I guess, still in the beginning. And I think there are a lot of exciting examples how one could apply these techniques. And I want to refer to this recent perspective paper led by Jakob Runge in Nature Communications, where actually he gives quite a nice overview of the different techniques which are already out there, and also the different challenges and problems we are still facing. And I will also, through my talk, come back to this paper. Okay, so the outline of my talk is also very brief. So it's first I'm going to talk a bit like why I think we should use these causal inference techniques or machine learning in general. Maybe this is a bit more addressed to the climate scientists in the room. And then I will briefly discuss what these methods are. Again, I make it very general. And in the end, I will give some examples of how we can use this and which challenges we still face. And again, maybe this is where the machine learners can help. All right, so why should we use them? I like this example. This is from a paper by Marie McGraw and Elizabeth Barnes in Journal of Climate last year. And what they plot here is the lag regression of ENSO, so just an El Niño time series, on temperatures in, across the globe. So ENSO leads in time, and they just do the regression, and everywhere where this regression is significant for some kind of significance test, you have this red dot. From this, again, you can conclude that ENSO really impacts temperatures across the world, or especially North and South America, but we also have some red dots here in Western Africa. But actually, if we do the same regression, but now temperatures lead in time, so you do this exact same thing, but just you take temperature at each grid point and kind of check how this regress on ENSO, you get the same plot. So this is a problem because regression and correlation are still the standard techniques in climate science when we're trying to understand teleconnection pathways. So this is the standard technique. But the plot on the right-hand side is, of course, not physical, so there's no way temperatures in, in Brazil affect ENSO. Probably, maybe there is even, but well, not in this plot. Okay, and the reason why we get this these same patterns is, of course, it's actually simple to understand. It's just that the time series, or the ENSO time series especially, is strongly autocorrelated. So and these autocorrelation strengths can affect the correlation strength. And this is from this Journal of Climate paper in 2014. Just if you imagine you have two time series x and y, and they are both, so you have autoregressive models. So x depends on itself at lag 1, and y depends on itself, but also on x. When we do something like regression or correlation, what we actually want is this c in the equation, right? So we want the relationship between, or the influence of y on x is, the other way around, so of x on y is this c. But, again, so they're both autocorrelated. But if we plot the correlation, we can do this now, just plug this in, and this is what we get. What you see now, this correlation strength depends on C, but it also depends on A and B. So this is the autocorrelation factor. So this, just the autocorrelation will of course inflate, or can inflate the correlation between X and Y. And this is again a problem because climate data usually is strongly autocorrelated, especially tropical data, for example. Different problems are, like next to autocorrelation, is that we have common driver effects. So some process Z can drive both X and Y. Also, this can lead to high correlations between X and Y, even though there is not really a causal relationship. And there might also be indirect links. Well, you could argue that these are, of course, causal, but maybe you just find these, you interpret X and Z of drivers of Y, but actually just one is enough, or like one is contained in the information of the others. So all these examples shows you that just taking a bivariate correlation analysis is too limited. So we need to kind of, or in many application cases, we need statistics which take more variables into account. So we need some kind of multivariate statistical framework. And this is exactly where then these causal discovery algorithms might actually help. Okay, so what are these algorithms? Sorry. Again, in this perspective paper, there's different types of algorithms already explained. I'm focusing here only on one particular one and explain a bit more detail, but they actually share that they depend on this concept of conditional independence. So just to recall, I guess most of them have seen this before, but we call two processes, or you can think of time series if you want, A and B. We call them unconditionally independent if their the joint probability is the joint probability density is the same as the product of the of P of A, P of B. So the single ones. And just to visualize this, if you have this square and here the shaded area denotes the probability, you can see by I that A, the probability of A is roughly, or is 1/3. Now if we have process B happening, And so the conditional, the joint probability of the joint probability density of A and B is this where the two overlap, and you can hopefully also see that this overlap is exactly 1/3 of B. So in this example, A and B are conditionally independent, so it makes no difference. The outcome of A does not depend on the outcome of B. And the same holds if we have a third process C. So conditionally independence given C is just the same thing, but we have this bar which denotes conditioned on C. Again, in this example, A and B would be conditionally dependent. I have altered A little bit. But if we say that C happened, or we are in this C universe, you can see again that the probabilities don't, so the outcome of C makes, the occurrence of C makes A and B conditionally independent given C. And this can actually quite easily be measured in the linear case. Just for, if we can think of correlation, if we have A and B and we can kind of show this, the scatter plot, then just from by eye or by calculating the Pearson correlation, we can just say that these two time series are dependent. And for the conditional dependence, it's the same thing. So it's very easy to compute. All you need is a regression. So what you first do is to check whether A and B are conditionally dependent or independent. You would first do a regression of A and C. So this kind of explains how much variability of A is explained by C. And then you have some residuals. So it's this here. So this residual part is the part which is not the part of A which is not explained by C. And then you can do the same thing with B. And you get also some residuals, so the part which is not explained by C. And if we then correlate the residuals, this kind of shows you whether there's still some shared information in the two, or whether this maybe this correlation you found in the first place was only due to this influence of C. Again, this is for the as a linear metric. And so from this, we would then conclude that A and B would actually be conditionally independent. So everything can be explained by C. So kind of the aim of these causal discovery algorithm is kind of to, like just from data, reconstruct the causal structure of the processes. So kind of the input of my algorithm are different time series. And what I want in the end as kind of an output is something we call cause effect network. So I kind of want a graphical model where the nodes are the different processes and the links tell me how they are causally related to each other. And the best case, I also want the direction of the links. In this example, the red links means positive relationships, blue links mean negative relationships, and the number on the legs on the links stand for the different legs. And I will get this, and again, I will explain this in more detail in a second, by the so-called PC-MCI algorithm. And PC-MCI is an adapted version of the PC algorithm, which stands for Peter and Clark, right? And MCI is what Jakob then edited, which stands for Mutual Conditional Information. More details in these papers, but yeah, so PC-MCI again, the idea is that it will, in order to get from input to output, it will calculate partial correlations and kind of, but iterating through different combinations of conditions in kind of an optimized way. And again, the aim is to get rid of these spurious correlations and due to autocorrelation or common driver effects or indirect links. This is actually all it is. And so as an example, let's see how this works. So the first step would be something called estimation of the parents. So in this visualization, or now you see you have the different time series A, B, C, D, E, F. And the different dots now stands for different time realizations. So you have at time step t, up till t minus 5, but of course the time series are longer. And when we are, for example, interested in estimating the parents or the drivers of time series A, what we do first is we would just have no number of conditions. So number of conditions is 0. we would actually just calculate correlations of time series A with all other time series at different legs. So in this example, so it's just what's said here. So you calculate the correlation of B t minus 1 with A. The time lag is really important here, of course, because we assume that the effect is in the future, so or the cause lies in the past. So this is what gives us the direction of these links. So we only consider links, again, with the potential cause being in the past, which again is pretty physical. So again, we would just calculate correlations and find then some which are significant, again, for some kind of significant threshold or significant test, doesn't matter for the moment. And in this example, we would get like a first estimate of potential drivers of process A, like here shown by these bluish boxes. So it's would be, we find process A at leg t minus 1 and B and so on. And then we would now go from correlation to partial correlation and would increase the, would start with conditioning. And as kind of the first conditioning, we would use this process A, like kind of the first member of the set of significantly correlated time series, and would now start to calculate the partial correlation. So we would go through this set and check whether the correlation of B with A can be explained by the influence of A. So just taking out kind of the autocorrelation effect. Well, and again, we go through this whole set. And then we will find that some will disappear. So some of these correlations could actually be explained by this autocorrelation effect. Then we go on and we condition on the next one. So we condition on B. Again, some will remain significant, others not. And then, well, we go through all these possibilities and come up with a second set. Then we could actually increase the number of conditions, and we start with conditioning on two processes, A t minus 1 and B t minus 1. Again, again, just on here in these boxes. Some of these correlations we found in the first place would then also could be explained by this multivariate influence, others will not. And in this example, well, we would stop here because in this case, we have only 3 processes left, and so we cannot increase the number of conditions, or maybe we told the algorithm we don't want any higher number of conditions. So in that example, the algorithm converged, and we would call these 3 processes the parents of time series A. And then, of course, we don't do this only for A, but we do this for all the involved time series. So we get a set of parents for all these different processes A until F. And the second step, we would then actually want to use these conditions to kind of estimate the link strengths. So again, as an example, if we're interested in the influence of time C, or the potential influence of time series or process C on A at leg 2, let's say, so again, visualized by these dots, we would not just calculate the correlation of the two, but we would first conditioning out the influence of their parents. So the green boxes here were the parents we found for process A, and the purple boxes here assume these are the parents of time series C. So again, then we would just calculate the partial correlation of these to kind of get a better estimate of their relationship. Finally, we can again then do this for all the different time series and then visualize these different links in such a graph, what we then called causal effect networks, because now, at least with respect to the time scale and also of the involved time series, we can interpret this in a way more causal way than before. Again, there are way more technical details I didn't mention. Also some statistical problems with, especially with multiple testing, with the different parameters of the algorithm. I won't go into detail, but I will refer to these different publications. One which is hopefully out soon in Science Advances, but it's already on archive. I should mention this. And so there are already several publications on this topic, and there's also several tests on generic data, on also with real-world examples, comparison with other methods. So I don't think you can see anything here, but so this is just to show the performance of PCMCI, and this is for different network sizes, so from just 2 time series up to 100 time series, and this shows the true positives and the false positives, again tested with generic data. And key point here is that it has high detection power, so has even for high-dimensional problems, we still have high detection power, also like most of the true links are found. And at the same time, the false positives are kept at this wanted 0.5 significance levels in these examples. But maybe more convincingly is to go back to this example from the beginning. So we have this ENSO case, we have 1 time series for El Nino, and then we look at temperature here in British Columbia, in this region. And on the left, you see what you would get if you do this, or would look at the relationship with using correlation. And so you would, of course, get a high correlation between these 2 time series. Here, the node color stands for the autocorrelation effect. But you would also get this link from British Columbia to El Nino, which is a false positive. With PCMCI, actually, you only find this one. Also, you see that, this link is not as strong as before because it is the autocorrelation effect is regressed out. And then we added some different generic time series. So we constructed some time series Z such in a way that it depends on ENSO and some noise term. And again, for correlation, you have problems because everything is connected with each other. But PCMCI kind of gets this true links. And even when adding more time series, and here they are constructed in such a way that some of these W time series depend only on themselves, and others depend on themselves and the previous ones. Again, correlation will not help you, but PCMCI kind of gets this relationship also with different tests. So it's, let's say, well tested with this generic data. But actually, a different problem with climate data is that we know very, very few examples where we kind of know the ground truth. So in this paper, we choose El Nino because it's probably, well, most climate scientists will agree with you that this is the that El Nino influences temperatures, but not the other way around. But then if you keep on thinking about different examples, it's actually not that easy to come up with some. So again, need for new methods and algorithms to kind of understand these processes. I will now come to the final part of my talk and actually show some examples of how we applied these methods to real-world data and how which other challenges there still are to face. But before I will just quickly show these different assumptions and potential pitfalls which come with these methods. This is discussed in detail in this paper by Jakob in Chaos. And I will not go into detail, but just if you look at the first and the second, or maybe the first 3 ones. So causal sufficiency is one assumption. So it means that we have we need to consider all the relevant factors. We also, the dependence assumption might lead you into problems. So I only looked at linear, I only used linear metrics, but what if nonlinear relationships are playing a role? I mean, all these, I'm showing this to show you, first of all, that you should be aware of the assumptions, and second, that with real-world data, you will always have problems. They will never be fulfilled, right? So it's always a compromise, and I think the only way to kind of solve this, or it's not giving up and not use it at all to real-world data, but it's actually to kind of be aware of the problem and to rely on expert knowledge, as we, I guess, which is also what Michael Gill said. So I like this, well, this comic, but also this little talk in EOS by Ebert, Uphoff, and Deng, where they kind of describe how data scientists and climate scientists can actually successfully work together. And the key is that they should talk to each other and that they should understand the methods and problems and the data from the other side. So I think, probably the only way to go. And in this context, I also want to show this picture again from the beginning. Again, I mentioned this is very problematic because we use regression all the time to understand teleconnections. But actually, a climate scientist would never believe or would never interpret this plot as temperature causing ENSO. And this seems very simple now, but actually I think there's a lot of value in this. So we should use the physics we already understand to get meaningful results out of machine learning applications. Maybe one of an example, this where I think causal inference in particular can help is actually hypothesis testing. And this is something I did in my during my PhD. And I looked at two different hypotheses which were out there and are still discussed in the climate science community. And so one by Kim et al. Looked at low Berenson-Karras concentration. So this is in this region roughly. And the related increase in turbulent heat fluxes due to sea ice loss. And the other one was given by Cohen et al., who looked at increase in Eurasian snow cover in autumn in this region. And both studies proposed that these changes in the polar region, which we observed, affects our weather in the mid-latitudes. And in particular, they showed, or they claimed that this change in the Arctic region leads to increased blocking in this Ural region. So you have this high-pressure system here. This high-pressure system then interferes with the climatological waves in such a way that there's increased vertical wave activity fluxes into the stratosphere, so the atmospheric layer above the troposphere where the weather takes place. And when we have these enhanced vertical wave activity fluxes into the stratosphere, this affects the stratospheric polar vortex. This is kind of a second jet stream, but in the stratosphere. And when all these fluxes come and the waves are absorbed in the stratosphere, this can then lead to a weakening of the polar vortex. And when we have this weak polar vortex, this can then affect, again, tropospheric circulation. So this circulation anomalies descend to the troposphere again, where they kind of lead to something which is called a negative Arctic oscillation. But you can think of this like southward shifted jet stream. And you have usually then cold air outbreaks over Europe. You have more precipitation and so on. So these are like quite impactful events. And so both these mechanisms connect the Arctic to mid-latitude weather via this stratospheric pathway. And these hypotheses are part of a bigger scientific debate in what way changes in the Arctic due to climate change actually affect our weather. And this is, like I said, still a very controversial topic because there are really different results with different model studies. So some models really tell you the Arctic plays a big role, others tell you it has no influence on our weather. So that's why we choose this causal effect network approach to kind of test these hypotheses with a different method, kind of give a complementary view on this problem. Again, first step, kind of to test these hypotheses, just using data and not using climate models, was to translate these different involved processes into different time series. So what I first was to kind of reduce this complex problem was just to create time series. I created one for Berenson-Karras concentrations, one time series for snow cover over Eurasia. Then there was one for sea level pressure over the Ural Mountains, one for over Siberia, one time series for vertical wave activity fluxes, one which captures the strength of the polar vortex, and then one for the Arctic oscillation. So in total, this gives you 7 different time series. This is here monthly anomalies, and, mostly reanalysis data. And kind of, these time series are already proxies for the involved processes. And also the time scale, let's say the choice of the time scale was not trivial, but on this monthly time scales, it kind of makes sense because this is exactly where we kind of expect these different processes to happen. Now the bigger challenge is, can we just, based on this data, kind of reject or confirm these hypotheses? And so we applied the PCMCI algorithm with different configuration, different timescales. And I will only show some of the results. We have some more, but I will focus on kind of the key findings. So what we found was when looking at this cause effect network in winter with these time series, we did actually find that this Ural sea level pressure leads to increased vertical wave activity. Vertical wave activity fluxes into the stratosphere. Then we also found that this leads to a weakening of the polar vortex, kind of as expected. What was more surprising, was that Berenson-Carassias concentrations, this was not surprising that it's extremely strongly autocorrelated. Again, here shown by this dark red node. But even when we take out this influence and when we consider this, and we regress out this influence of the autocorrelation of Berenson-Carassias concentration, we still found a significant influence of Berenson-Carassias concentrations in autumn onto this Ural sea level pressure pattern. So indeed, we could really, using this method, confirm that this low Berenson-Carassias concentrations in autumn leads to a weakening of the polar vortex in winter via this increased Ural sea level pressure pattern. For snow cover, again, this was also discussed. We did find some links, but overall the results were way less robust. So yeah, kind of saying that our analysis cannot support such a statement. But again, this remains a controversial topic, but in the meantime, there were also several modeling studies which kind of find the same link. And again, I don't think this is meant to get rid of targeted modeling experience, because this is basically the only thing we have in climate science. But it's rather to show that this can be really a complementary approach, kind of to link observation and model studies and kind of to give a different perspective. This was one example for hypothesis testing. Maybe a second example, which is relatively straightforward, is that the issue of statistical forecasting. So again, I will keep this example of the polar vortex. And there are different processes which are known to affect variability or the strength of the polar vortex. Again, some of them might interlinked, or there might be common driver effects and indirect links. So if I would include all of them, I would definitely lead into some overfitting issues. And you can visualize this, let's say here. So we have an index of interest which we want to predict. And we have different precursors, so we're just lagged in time. And they're correlated with this index of interest. Using all these precursors leads to overfitting. But since I have an algorithm which kind of can identify these spurious correlations, I can just use this to kind of find the causal precursors among all these precursors. And these causal precursors should then, in theory, also be my better predictors without having this overfitting issue. So we did this and applied this to the polar vortex. So what we did, so here, my index of interest, again, is this polar vortex time series, these winds in the stratosphere. And in this case, the time scale are means of 15 days. So I have different bins of 15 days and just average over them. And then the first step, kind of to get all precursors of these polar vortex time series, was to find all the correlations, so also the spurious ones. So we calculated one-point correlation maps at different lags, where we would expect an influence of different fields, such as sea surface temperatures and sea level pressure, geopotential heights at 500 hectopascal. This is V prime T prime and 100 hectopascal is where you have this vertical heat fluxes, and also winds in the stratosphere. So basically, we included those fields where other studies already mentioned to be relevant. We can zoom in on one of these plots. So this is a one-point correlation map of sea level pressure at lag 2 with this winter polar vortex time series. What you see here is, so this Ural sea level pressure region, so this is Europe, Africa, and you have this region of positively correlated sea level pressure. Again, this think of this Euro blocking, what we found before, so this makes sense. But we have also many different regions which are significantly correlated, here shown in contours. To kind of reduce this, these fields, we only constructed one time series index per significantly correlated region. So we would get one index, one time series for this region, one for that, and so on. So in total, we have almost 500 different time series, or 471 of different precursor regions, which just by construction are significantly correlated with my polar vortex time series. We put all these time series and ran the PCMCI algorithm, and actually then only 4 of them were identified as causal precursors. So most of them, or almost all of them, could just be explained by these different autocorrelation or common driver effects. What was robustly found was that the polar vortex itself at leg 1 plays a role. Physically, this makes a lot of sense. So it's the state in the stratosphere which matters. Then we also found these 2 regions of vertic wave activity fluxes. So again, this is the waves which enter the stratosphere and then break in the stratosphere, and then break, and are absorbed by the polar vortex. These were also found as robust causal precursors. And when we also found one region of sea surface temperatures here in the tropic Western Pacific, which we think is related to the Madden-Junior oscillation. Again, and these we could just very easily use as our regressors and just construct a very simple multivariate regression model. You could, of course, also think of other methods, but just with regression, it actually worked fine. So this was our very simple prediction model. And when looking at the performance, so what we did, this is the time series of the polar vortex observed over the last almost 40 years. And then we split our data into a training and a test period, and we used this method, or we trained this only over this test period. So the whole algorithm was only run over this period, and so also the regression model was only trained over this period. And we would actually get, fits very well, high correlations. But even if we then go to the test data and do one step ahead predictions, the correlation didn't drop, meaning that we have confidence that we kind of found physical, meaningful predictors. Where the stratospheric dynamicists in the room would not be impressed by this at all, because it's just known from stratospheric dynamics that it's the vertical heat flux and the state dependence in the stratosphere which matters. But again, here the purpose of this paper was more to kind of show how that this algorithm works, and that even if we put in 500 different time series, it would find, in this example, it would find the relevant ones which we can also interpret in a physical way. We called this response-guided causal precursor detection scheme. Maybe not the best catchy name, but it's out there already, so it's called like this. And we then applied it also to the Indian summer monsoon. This was recently published by Di Capo et al. In Weather and Forecasting, where we actually found out that it's not so easy and doesn't work as well when you apply it to the Indian summer monsoon, because you have different problems. And for example, this assumption of linearity definitely does not hold when it comes to the Indian summer monsoon, because it's heavily impacted by ENSO, for example. So in this paper, what we then tried is more to go to state dependencies and kind of split data into ENSO phases, El Niño phases, and La Niña phases, and kind of better understand what's happening on these subseasonal timescales when we focus on different background states. We learned definitely also more about both the method, but also about the Indian summer monsoon and the dependence on ENSO. We also have right now applications for Morocco crop yield and hurricane activity. And again, each time it's not as easy as just putting data into and then get meaningful results. It's always harder, and looking again at the data and so on. So again, my key message here is that the data and the processes you look at really matter. And it's also available on GitHub. So Sam, who's also here, put it on GitHub and actually works a lot on making the algorithm better and faster. So if you're interested in getting involved, talk to me or talk to him. Yeah, so still have some time, 3 minutes? Wasn't it an hour?
It's an hour.
Okay, well,
10-minute discussion.
all right, so I make it's the last example, I promise. So 10 more minutes is fine? Or what?
We can have 10 minutes. You're until 2:30 and...
I'm quick. All right.
11 minutes for this minute for discussion.
Okay, good. All right, so last example, I think this is actually also work in progress, so I won't go into detail because the results are not are not final yet. But it's the issue of process-based model evaluation. So just to show you on the left, this is actually the projected strength of the polar vortex in the CMAP5 ensemble. So you have different climate models, and then you want to ask, okay, how will the polar vortex at the end of the century be stronger or weaker than right now? And what you get is, well, the median says it won't change at all, but this is only because roughly half of the models will say it will strengthen, and the other half says it will weaken. Okay, so but and this is actually relevant because like this uncertainty in the projected polar vortex time series was shown to actually account for much of the uncertainties of weather in Europe and North America. For example, it's much of the uncertainties regarding Mediterranean precipitation come from these uncertainties of the strength of the polar vortex. So what we really want is kind of a method to kind of have to better understand these ensemble spreads, but more looking at the different process, the dynamical process which play a role here, and kind of assess this using different statistics. So so my data here right now, also we do this again with causal inference techniques, and my data is very different. So now I have different models, and for I think it's not even complete, but it's different climate models from the CMAP5 ensemble. And I can actually do the kind of same network analysis each time, but including these, I'm interested in the, sorry, I should have said this before. So I'm interested in the role of the potential role of sea ice for this ensemble spread. So maybe it's the capability of the models to either capture or not capture the sea ice stratosphere connection, which might lead to this ensemble spread. Just looking at the ensemble won't help us, so we have to kind of go into the different processes and kind of test whether or not they are represented by these different models. So what I did is kind of repeat this analysis, but for each model differently, and then I can just compare the causal link strengths for the different models instead of comparing climatologies and so on. So just quickly, I could just look at how well is this link from vertical heat effluxes to the polar vortex represented. And I would actually, this shows the distribution of the link strength across the different models. You won't see much here, also the strength doesn't matter for this moment. Just to say that this is actually captured by all models, it's captured pretty well. When it comes to this link from Ural sea level pressure to the vertical wave fluxes, it's actually also captured relatively well by most models. And when it comes to sea ice, most models do capture it, but well, preliminary results, let's say, I would say that it seems to be too weak. But again, this is not the end of the discussion. What I want to say is that kind of this method really gives you the opportunity to kind of trace back the different processes and different steps and kind of better understand what goes wrong, where, and why. Now I'll finish. Oh, sorry, I won't finish. Just quickly, this is from the from the perspective paper. Actually, there's this graph here where you have a list of many different challenges with causal inference in earth science. So it contains a challenge with the different processes, such as autocorrelation, time delays, and so on, but also with data. So, for example, the issue like how can we kind of the best way to construct these different climate indices. I mean, what I showed with the RGCPD algorithm is just one way to do it, but there might be other or better ways to do it, and also some computational issues. So please have a look at this paper, and get involved. Another way to get involved is by this causme.net homepage, which was launched together with this paper. It's not related only to climate data, but to any kind of data, right? So you can get involved either by developing a new method and test it with the data which is provided on the homepage. Or you can provide data where you know the known the causal ground truth. Again, this is not so trivial for many, at least in climate science, but maybe for you have other data sets where you know the ground truth, then this would be really good to kind of test the different methods and see how they perform. And now I will just quickly summarize. So I think we should use them because understanding teleconnection is really key, not just to make better forecasts on S2S timescale, but this is one big example and where it can really make a difference. And machine learning can definitely help here. So I use these causal inference techniques, especially PCMC algorithm, which are one way to better understand these processes. And they are useful for, or you can do different applications like hypothesis testing, statistical forecasting, or model evaluation. But again, said one last time, I do think that the knowledge of the data is relevant or is important here to get actually meaningful results, because we know that there are heavy assumptions on the methods, but also that you cannot just use the methods just to get rid of the physics. You just need both ways to understand something. And now, thank you.
Hi, thank you very much for the well-explained presentation. So I have one question regarding the conditioning of mutual information or conditioning of any other method, for example, transfer entropy. So when you condition, does it really remove the influence of the third variable, or sometimes it has the tendency to give synergy effects by by giving over information flow or under information flow? So does the conditioning really remove the influence of the third variable? That's my first question. The second question is when you kind of do conditioning of multiple variables, let's say. So then we have the limitation of the time series where we are always limited with the number of time series length for the climate data at least. So how do we overcome this problem? So I just want to learn these two aspects from you.
Sorry, could you repeat the second question?
Yeah, just about the time series length. When you condition out different variables, you need to have good enough of length of time series to make PDFs and so on. So how can we overcome it? So I just want to learn these two aspects from you.
Maybe to start with the second one. Yes, I mean, of course, longer time series definitely help. I mean, with observation data or real analysis data, it's only 40 years, so it's not a lot, especially, I guess, with nonlinear metrics then. For different significance tests, this might be a problem. I mean, with climate models, good thing is you have a lot of data and you also have long time series. So actually, for example, in this example for model evaluation, I also use model data to kind of get estimates, or with the historical runs to get estimations of the uncertainties of the link strength within the observations. So I guess this might also help to kind of not only to use observations to evaluate the model, but also the other way around. The other thing, I guess, also depends again on the assumptions. If it's linear, it should get rid. There can definitely be synergies, and I think especially thinking of compound events, where I don't have a plot here, but it's also in this perspective paper. There's a nice visualization that it's maybe only if A and B are in a very extreme state that they will lead to cause C, but not it's not the variability. Just removing A won't show you this, but it's really the synergy of the two. So I would say it's not perfectly contained right now. So maybe another example of getting involved.
Okay. Marlene, thanks a lot for your very brilliant and clear talk. It was very convincing. So I have two questions. So my first question is your causal network approach. How different is it from learning a Markov chain description of the relation between your variables? And the second question is, as already has been discussed a bit, but you will have problem because of the subsampling, because of the lack of data. So could you consider specific methods to actually, for instance, resampling, or specific methods to actually sample better the links that are missing in
So like, let's say the more method answer of this, I would actually really refer to Jakob. I think he will answer this way better than me, because I don't know. I mean, how we dealt with this a little bit, let's say, at least in this hypothesis testing example, is when we had this subsampling, or where this time scale issue, is that what we just did was to construct the networks also for different time scales, and went from monthly to half monthly to weekly, and to kind of see how robust the structure was, and where would we actually find links, and where would they disappear, and then again, how can we interpret this? So I think this is not, it's really more like an example from the climate science side of how you can address this in kind of doing sensitivity analysis, because for example, the link from the stratosphere to the AO, we didn't find them on monthly timescales, but actually on weekly timescales. So I think this is one way to address this. From a methodological point of view, not sure. But I guess can be discussed, especially with Jakob and others.
Okay, let's thank Marlene again. And of course, you're welcome to